Welcome to lecture 24. This is the final lecture on virtual memory. We are going to be talking about ways to make adverse translation faster using a structure called TLB. A quick note on the final exam. So the final exam will be administered through Gradescope. We will soon release a practice exam to make sure that you're familiar with the interface. And regarding the topics, a strong emphasis would be placed on the topics that we covered after the midterm. So that includes pipelining, branch prediction, caches and virtual memory. We should have final exams on the website, which you can use as a reference to practice few more problems. Okay, so let's quickly recap the key concepts in virtual memory that we need for today's lecture. So virtual memory, like we talked about, is an idea that allows programmers to visualize and access a very large memory space. So from a programmer's point of view, which is defined by your ISA, in this example, the programmer gets to see 2 to the power of 20 bytes of memory locations, and that is because the virtual address is of size 20 bits. The physical memory, like we talked about, is defined by the computing system that you have. So your physical main memory may be much smaller than your virtual memory. So in this example, it has only 16 kilobytes. In addition, you may have allocated space on your disk, and that space can be changed by configuring your operating system. Now, at any given time, when an operating system is requested to create a process, it would create a new process, and as part of that process creation, it would create what is called as a page table. A page table is nothing but a data structure that contains a mapping between a virtual address to the corresponding physical address. Every process has its own page table, and that's how the operating system makes sure to isolate the addresses of different processes. So one process cannot access the physical memory that has been allocated to a different process. So today we want to focus our attention on this address translation process. So here I have a cartoon that simply represents how a virtual number is translated into a different virtual number, and like we talked about, the page offset remains a constant. So the address translation requires that you translate a virtual page number to the physical page number. Now, this address translation process has to be done for every memory access. Now, we need to make a memory access for every load and store instruction. So this will be done as part of the memory stage. But keep in mind that every instruction has to go through this instruction fetch stage where you retrieve the instruction from the memory. So you also have a memory access and in the fetch stage. Whether it is a load or a store or a branch or an add instruction doesn't matter. Every instruction has to come from memory, and therefore you need to access memory, and therefore you need to do an address translation. So in the case of a non-load or store instruction, you have one memory access through instruction fetch. In the case of a load store instruction, you have an address translation at the instruction fetch and one more in the memory stage. So the point is, the address translation is an important step that defines a process's performance. So what is involved in the address translation? Well, we said we need hierarchical page tables in the last lecture because we don't have space to have a single level page table. So in modern systems, you use at least 3 levels of page table. And so if you're going to use 3 levels, then to perform one address translation, you need to look into 3 different page tables, right? First level, second level, and third level. So 3 different page tables need to be looked up to perform one address translation. So clearly that is expensive in terms of amount of time that will take. In this example, even for a single level page table, you need to go to the main memory, and that could be expensive. So the main problem that we are going to talk about in this lecture is this problem of address translation overhead. Address translation is very important because it is on the critical path of an instruction's execution. It can be done only after the virtual address is known. Clearly, because you don't know the virtual address, then you can't really translate it. So you need to wait for the address to be known. So in the case of a load or store instruction, the execution stage is the one that would compute the virtual address. And in the memory stage, you need to then translate it. And the translation has to be done before accessing the memory hierarchy. Now later on we'll come back and optimize this particular constraint, but for now assume that you have to do the address translation after the address is known, and then only you can go and access the memory hierarchy, which includes your cache and then your main memory. And we just said that an address translation can be expensive, especially if you have a multi-level hierarchical table, because you need to perform n additional memory lookups. So what's the solution? Well, the solution is to avoid going to the main memory for accessing the page table. So we want to cache the page table. So we could just simply cache the page table in our regular caches. That's one option. But then we are going to pollute our regular data that the program is going to access, and maybe it is not specialized enough to exhibit good amount of locality for the page table that we want. So modern processors have a special cache called TLB, and that TLB is meant to cache only one data type, which is page tables. And it's meant to speed up the address translation by reducing the number of main memory accesses to page table. So it is, what is a TLB? Well, let's talk about that and then come back and talk about how large it typically is, etc. So this is how a page table cache looks like. So a page table cache, remember what a page table has. So a page table, it could be multi-level, but for now assume that it's a single level page table. You take a virtual address, and then you would have the physical page number that is stored in the page table, and that's what you want to produce as the output. So what we want in the cache is the physical page number. That's the data that you want to cache, right? And so that's exactly what we have done here. So we have the virtual page number that is indexed into this array, and then each entry in the array corresponds to an entry in the page table. Now what you will notice is that each entry has this thing called tag. Now this is effectively a very simple cache. If you go back to our first lecture on cache, we talked about tag array and a data array. This is way before we even talked about cache blocks, where we said for every address you keep its data item, and the address would be essentially what your tag is. So in this case, the virtual page number, the entire virtual page number, is treated as a tag, and the data item is just the physical page number, meaning just one data item. So if the physical page number is 2 bytes, then your cache block size is just 2 bytes, right? So in this case, I'm not really exploiting any type of a spatial locality at all, because my cache block size, TLB block size, is effectively just one page table entry. And there is also one more thing which is true, which is also true about the simple cache that we talked about at the beginning of the cache lectures, which is this structure is fully associative typically. And this allows a given virtual page number to be stored anywhere in the cache, and that's why we have the entire virtual page number as a tag, so VPN, and it can be stored anywhere. So that means when you do the address translation through TLB, you got to do a fully associative search, so you need a parallel comparisons to all the tags that are stored in this structure. Okay, so this is a very simple cache structure that caches different entries in the page table at the granularity of one page table entry. Now, you may be thinking about what happens in the case of a multi-level page table. Do I cache intermediate state of first level, second level, third level page table? Well, actually, the answer is much simpler. So you don't cache the intermediate page table entries, but you just store the final translation. So if you remember the lecture on hierarchical page table, what you do is first you access the first level page table, and then you access the second level page table, and then you access the last level page table. Let's say if you have 3 levels, and so eventually the last level, the leaf would tell you what the physical page number is, and that's the answer that you're looking for to translate a virtual page number, right? So I'm not really interested in the address to the second level page table from here. I'm not interested in the address to the third level page table. What I'm only interested in is the physical page number. So this is what I need. Given a virtual page number, I need to translate that into a physical page number. All that hierarchical table allowed us to do is save page table space in main memory. It's purely a space optimization and nothing more, and we gave up by requiring more memory accesses to do that translation. But fortunately, when you have such a cache like TLB, you can get rid of those intermediate steps and simply cache the virtual page number and the final answer, which is the physical page number corresponding to that one. Right? So to summarize, a TLB is nothing but a fully associative cache. Each entry is a page table entry that translates a given virtual page number to a physical page number. And because it's a fully associative structure, it has to be fairly small. You cannot afford to have thousands of entries in it, because then your access would be much slower. And therefore, in modern systems, TLBs are typically small. It caches only 512 entries. Now you might be saying, well, that's too small. Then the cache hit rate may not be, or rather the TLB hit rate may not be high. But that's not really true. If you think about it, if I have 512 entries, that corresponds to 512 pages. So I can translate any address in 512 pages using just 512 entries in the TLB. And if I say each page is of size 2 to the power of 12, which is typical size of a page table in modern operating systems, which is 4 kilobytes, then this is a fairly large amount of address space that you're able to translate with a very small structure. And that's why even with the small TLBs, the TLB miss rates tend to be much low.